Hello everyone. So this is a presentation on thermodynamics of micellization, which deals with micelles, surfactants, how they interact and how micellization occurs, and an experimental procedure conducted to study the thermodynamic parameters of micellization. I, Kumar Sambhav Rath, and my lab partner, Ms. Divleen Kaur Bhatia, students of Postgraduate Department of Chemistry, Indian Institute of Technology, Delhi, have constructively prepared this presentation together. So, this discussion involves two parts. First part is introduction to surfactants, their properties, structures, interaction with solvents, and theory behind micellization and uses of surfactants, which is going to be covered by Divleen. And the second part, thermodynamics of micellization, CMC, fractional micellar ionization, experimental procedure to study the micellization, and discussion on the result obtained is going to be covered by me, Sambhav. So now let's jump into the discussion.
First, we are going to discuss the theory behind this experiment. So, the first question arises is what are surfactants? So, surfactant is also called surface active agent, substance such as detergent that when added to the liquid reduces its surface tension, thereby increasing its spreading and wetting properties. In the dyeing of textiles, surfactants help the dye to penetrate the fabric evenly. They are used to disperse aqueous suspensions of insoluble dyes and perfumes. The surface active molecule must be partly hydrophilic and partly lipophilic. That means water soluble and soluble in liquids, respectively. It concentrates at the interfaces between bodies or droplets of water and those of oil or lipids to act as an emulsifying agent or the foaming agent. Now, there are four different types of surfactants known as non-ionic, cationic, anionic, and amphoteric. So these surfactants differ in the composition and the polarity. As you can see, the cationic having the positive charge, anionic having the negative charge or in the hydrophilic part, and the amphoteric having both positive and the negative charge. Okay, now moving to the structure of the surfactant. Now, surfactants are substances that with the molecular structures consisting of hydrophilic and hydrophobic part, where head part is hydrophilic that is attracted to water, or you can say water loving, or the tail part is hydrophobic that means repelled by the water. Oh, and now, so the hydrophobic part is normally a hydrocarbon that can be linear or branched, whereas the hydrophilic part consists of ionic or strongly polar groups, example polyglycol ether groups. So due to this characteristic structure, these compounds have a special property, namely the interfacial activity, that sets them apart from the organic compounds in general. So surfactants will diffuse in water and adsorb at interfaces between air and water or at the interface between oil and water. In case where water is mixed with oil, the water insoluble hydrophobic group may extend out of the bulk water phase into the air or oil or into the oil phase, while the water soluble head remains phase in the water phase because the hydrophilic part is water loving. Now coming to the examples of surfactants, sodium stearate is a good example of surfactant and it is the most common surfactant you can find in a soap. Another common examples of surfactant is 4,5-dodecyl benzene sulfonate. Other examples also include docoside, that is dioctyl sodium sulfosuccinate, alkyl ether phosphates, benzyl alkonium chloride, that is also called BAC. Now coming to the how surfactant work and form Michels. So surfactants adsorb at interfaces as we have discussed earlier. So surfactants adsorb at interfaces and due to this amphiphilic nature, surfactants adsorb at the air water or oil-water interface. At the interface, surfactants align themselves so that the hydrophobic part is in the air and the hydrophilic part is in the water. So for our simplicity, I'm going to consider the air-water interface. So the cohesive forces between the water molecules are very strong due to the hydrogen bonding, so its surface tension is very high. As the surfactant absorb, they break these interactions. The intermolecular forces between the surfactant and the water molecule are much lower than the between two water molecules because those are hydrogen bonding and these are just the interaction. Therefore, the surface tension will decrease. So when the surfactant concentration is high, they will form micelles. The point at which micelles are formed is called critical micelle concentration. So the main purpose of surfactant is to decrease the surface and interfacial tension and stabilize the interface. Now, as we have mentioned in the previous slide that what critical micelle concentration. So what is critical micelle concentration? The critical micelle concentration is the exact concentration of the surfactants at which aggregates become thermodynamically soluble in the aqueous solution. Below the CMC, there is not a high enough density of a surfactant to spontaneously precipitate into distinct phase. And above the CMC, the solubility of the surfactant within the aqueous solution has been exceeded. And now we are going to discuss this figure. So as you can see that at low concentration, there is low concentration of surfactant, there is moderate surface tension as there are not many surfactant molecules on the surface of water. But as you increase the surface surfactant concentration, the molecules on the surface increases and the surface tension decreases. On further increasing the concentration of surfactant or at reaching the CMC, that is critical micelle concentration, micelles are going to form and surface tension will decrease. On further increasing the concentration, that means greater than the CMC, the micelle formation will increase and hence it start forming the aggregates and start getting precipitated out, and the surface tension will also get lowered. Another factor that can uh, affect the surface tension can be the effect of concentration and temperature. So, specific temperature at a specific pressure at which large groups of micelle begin to precipitate out into a quasi-separate phase. So, as we increase the temperature, cloud point this above the cloud point, this causes the distinct surfactant phase to form densely packed micelle groups known as aggregates. So basically, if you increase the temperature, the aggregate formation will also increase. And if you increase the concentration also, the aggregate formation will also increase. Now coming to the applications and the uses of surfactants. So, the annual global production of surfactant was 13 million tons in 2008. In 2014, the world market for surfactants reached a volume of more than US $33 billion. Now, coming to the uses of surfactants. A vast range of surfactants like emulsifiers, foaming agents, and wetting agents are utilized based on the areas of use. Surfactants minimize the surface tension with respect to the phase and hence lie at the heart of the interfacial chemistry. So, surfactants play an important role in cleaning, wetting, dispersing, emulsifying, foaming, and anti-foaming agents. It is also used in agrochemical formations such as herbicides, insecticides, biocides, sanitizers, and spermicides. Personal care products also have surfactants, like in the products cosmetics, shampoo, shower gels, hair conditioners, and toothpaste. Surfactants are also used in firefighting and pipelines where it is called liquid drag reducing agents. Alkali surfactant polymers are also used to mobilize oil in oil wells. Surfactants are sometimes also added to the car engine lubricants, which greatly help to keep particles from sticking to the engine parts. Also, surfactants commonly used in corrosion inhibition in ore flotation.
So now let us begin with the experimental procedure to study the thermodynamics of micellisation, and let us see what all we have to do in this experimental procedure. So as we saw that the micelle formation occurs due to the aggregation of a huge number of surfactant molecules, and the hydrophilic end or the water interacting end stays outside, and the hydrophobic end or the organic part or the non-polar part stays inside the micelle pocket. So in a simple dissolution of a surfactant molecule in water, it stays as a solvated molecule and its properties will show a regular behavior with this concentration of the molecules. As the concentration increases and reaches a certain value, the variation of such properties with respect to the concentration changes abruptly, and this happens due to the micellisation. And as we can see that when micelles are formed, the number of molecules or the number of particles per unit volume decreases, and thus the bulk properties, which can be conductivity or surface tension, etc. These can decrease with respect to concentration on micelle formation. Now, this point where the micelle formation occurs and the concentration corresponding to it is known as the critical micelle concentration, as discussed before. This change in behavior occurs due to the aggregation of a huge number of surfactant molecules due to the formation of micelles. Now, for this, we have to find out the critical micelle concentration first, and this can be done by conductivity measurement. As we saw, different bulk properties like surface tension or conductivity depend on concentration. Now, conductivity being a bulk property changes with the concentration, and as we change the concentration and measure the conductivity values, a linear variation is obtained. But at a point, this linearity is violated and another linear behavior with a different value of slope is observed. And this is due to the micelle formation. And that break point, if we plot a graph between the property, the bulk property, and the concentration of surfactant, then we will see that two lines will intersect each other at one point, and that point is known as the micelle formation point, and the surfactant concentration corresponding to it is known as the critical micelle concentration. Now here we are using sodium dodecyl sulfate as the surfactant molecule, which is abbreviated as SDS. Now, and the concentration of SDS corresponding to this point is the CMC, critical micellar concentration, and SDS is an anionic surfactant, and the dissolved molecules remain in the ionized state. Now on micelle formation, what happens? As we saw in the previous picture, the hydrophilic head stays outwards and the hydrophobic head stays inwards. The sodium dodecyl sulfate molecule is an anionic surfactant, and we can expect that these hydrophilic ends will be anionic in nature because these will be containing negative charges which are neutralized by a sodium ion in the free molecule. Now what happens in the micelle formation? This is a spherical molecule, and in this spherical structure, on the surface of the sphere we will be having saturated negative charge density. So to neutralize this negative charge density, some counter ions get absorbed on it. The fractional micellar ionization alpha is obtained by dividing the latter obtained slope by the previously obtained slope. The fractional micellar ionization indicates the ionic charge neutralized by the counter ions at the surface of the micelle. So this value of alpha is important in order to know that how much of charge is being neutralized by the counter ions of the micelle, but not the free molecules of surfactant. So we can establish an expression of equilibrium like this, that during micellization, n number of sodium dodecyl sulfonate ions or the surfactant ions plus n alpha number of sodium ions, that is represented by A plus, stay in equilibrium with micelle molecules which aggregate with n number of surfactant molecules and have the charge minus of 1 minus alpha n. So here CMC is the concentration corresponding to the intersection of two lines, and the fractional micellar ionization can be given as alpha is equal to slope of line after CMC divided by slope of line before CMC. Now from this equilibrium expression, we can calculate the K equilibrium if we know the concentrations of these values, and we know these species, and we know these values, the N alpha and this concentration. Then K equilibrium can be given as the micelle concentration divided by surfactant concentration raised to the power its coefficient, that is N, multiplied by the ion concentration raised to the power N alpha, that is the number of ions getting adsorbed on the missile surface. So K equilibrium can be approximated as missile concentration divided by A plus CMC raised to the power 1 plus alpha multiplied by N, where A plus minus CMC is the mean activity of S minus as well as A plus. So this is an approximation we can make. Now from this value of K equilibrium, we can find the change in Gibbs free energy due to micellisation, and from that we can find the other thermodynamic parameters such as enthalpy change or entropy change, etc. Now we know that Gibbs change in free energy is given as delta G is equal to minus RT ln K equilibrium, and in the above equations N is a very large number because a large number of surfactant molecules aggregate together to form the micelle. So from these expressions, by different approximations, we can eliminate n, and finally the delta G becomes dependent on alpha and the CMC concentration. So different approximations can be made in calculation of delta G, and also we can find out delta H from calculation of delta G with the help of this equation, that is delta H is equal to minus T square delta of del of delta G by T divided by del T. So using these equations, we can get the final expressions of change in Gibbs free energy, change in entropy, and change in enthalpy, which are delta G naught of micellisation is 2.303 RT 1 plus alpha log CMC. Delta H naught of micellisation is equal to minus 2.303 RT square delta 1 plus alpha log CMC by delta T, and delta S naught micellisation is equal to minus delta H naught micellisation minus delta G naught micellisation divided by T, which comes from the Gibbs-Helmholtz equation. Now here in the expression of delta H naught micellisation, we can see that inside the differential term we have kept the alpha term as well as the CMC term. That means this alpha as well as the CMC vary with temperature, and that is why we have to keep it inside the differential term. Otherwise we have to consider the value of alpha or CMC as constant, which is not possible, and that is why we are conducting this experiment at two temperatures. Now the values of alpha and CMC can be known from the conductivity versus concentration graphs. The same procedure can be repeated at a higher temperature to get the values. These values enable us to calculate the above mentioned thermodynamic parameters. And let us look at the experimental procedure so that we can know what all we have to do inside the lab in order to get all these values, the value of CMC and the value of alpha. So let us look at the experimental procedure, which includes preparation of SDS solution of a known concentration, and here we prepared 50 millimolar concentration of SDS solution in 50 ml volume. Now we recorded the conductivity value first at room temperature, which was 37 degrees Celsius during that time. Dilution of the solution by removing 5 cc of solution and adding 5 cc of distilled water. Here what we are doing is we are removing some solution and we are adding the same amount of water. That means we are reducing the concentration by removing some solute or removing some solution and adding some pure solvent. So the concentration after that dilution can be given as C dash is equal to C naught multiplied by 1 minus small b by capital V plus small v, where small v is the volume of water added or the volume of solution removed, and capital V is the initial volume of solution taken, and C naught is the initial concentration which in the first step is 50 millimolar concentration. Alright, so then we will measure the conductivity of diluted solution, and after each step of dilution we have to dilute the same solution, the 50 millimolar solution, about 15 times. We have to dilute that solution 15 times, and for each dilution we have to measure the conductivity value. And these four steps were repeated for the same solution at a higher temperature. At 50 degrees Celsius, this experiment was conducted inside the lab. So we had the tables of conductivity and concentration for two temperatures. One is at 37 degrees Celsius and another was at 50 degrees Celsius. Now, graphs can be plotted between conductivity and concentration of sodium dotyl sulfate, and the graphs look like this. So here in these graphs, as you can see, at a lower temperature graph, as you can see, the first line slope is like this and the second line slope is like this. So as you can see that here we see a break point between these two lines. These two lines intersect each other at this point, and the sodium dotyl sulfate concentration corresponding to this value is known as the CMC. So CMC occurs somewhere around here. Now, at a higher temperature, if we see, the intersection of two lines occurs at this point, and the CMC corresponding to this point is around here. So, by placing these two graphs like this, we can see that at an increased value of temperature, at increased temperature, the CMC or the critical micellar concentration shifts towards the right hand side. That means the value of CMC increases. Also, we can see that the relative variation, the relative deviation of the second line with respect to the first line is lower in the first graph, that is at a lower temperature, and this deviation is higher in the second graph. So we can see that the angle between these two lines, the orange line and the blue line, the angle is more here and this angle is comparatively less here. So this will give us some results. So the results are as follows. The first result is, with an increase in the temperature, the break point in the graph was shifted towards the right, which means the CMC had increased with an increase in the temperature. Now below CMC, the molecules stay as individual non-associated hydrated molecules, and on increasing the temperature, it distorts their hydration sphere. So what happens is, the association and formation of micelles can occur at a higher degree of association, and as a larger number of molecules will be free from hydration, and that is why the concentration of SDS molecules at micellization point is more at a higher temperature. Now, the second observation made is, fractional micellar concentration or fractional micellar ionization alpha decreases with increase in temperature, which is shown in the changed angle between these two lines. As we discussed, the angle between these two lines decreases as we increase the temperature. That means the value of alpha decreases. Now, the third observation is, the overall effect of temperature on alpha and CMC results in a positive value of delta micellization H0. Thus, micellization is endothermic. If we look at the formula of delta H0 micellization, the differential term involves alpha as well as CMC. Now, CMC increases but alpha decreases. So, these two, as a product of each other, overall increase the value of enthalpy, and the delta H0 micellization is positive. That means this differential term becomes negative and delta H0 micellization becomes positive, which suggests micellization is endothermic. Now, the values obtained for delta S0 micellization and delta G0 micellization are positive and negative respectively, which favor the formation of micelles by shifting the equilibrium to right hand side. As we know from the equilibrium criteria, entropy change should be positive and the change in Gibbs free energy should be negative. Now, the high positive change of entropy can be explained on the basis of these 2 points. The first point is, as concentration increases, the molecules become less solvated and move into the hydrophobic pockets of the CMC. As we discussed before CMC, the surfactant molecules stayed as hydrated molecules, and when that hydration got removed, a huge number of water molecules got released from their binding, and this surfactant molecule entered into its pocket inside the micelle. That is why a number of water molecules got released, and that increased the entropy of the solution. And the second point is the hydrophobic group had an increased freedom inside the micelle pocket than that in the solvated state. So in the solvated molecule, a number of water molecules kind of bound the surfactant molecule inside a cage kind of structure, which got removed in the formation of micelle, and that is why the freedom of that micelle molecule got increased when that micellization occurred. So this increases the overall entropy. So this concludes our discussion on the thermodynamics study of micellization. Thank you.